Afternoon, folks. I appreciate that it might not be afternoon where you are, but it's afternoon as I'm recording this. Now, this video is going to be about the water balance, which is an equation and can also be shown in a graph and is often quite tricky. But before we get into that, those of you who do geography at college, hopefully you will find in your module booklet between the last video, which is about water in the sky, or sorry, the last section in your booklet, which is about water in the sky, and the section about the water balance, you should find a few pages of revision guide questions and past paper questions. And I want to say a couple of things about that. I'm not going to go through every answer at all. Firstly, I just want to pick up on the fact that there are some questions about drainage basins. Drainage basins are mentioned in the very first video for this module, so if you haven't seen that and you have no idea what a drainage basin is, I would go back and watch that video. But the question asks you about the source and the mouth of a river, which, to be honest, you can probably figure out for yourself. A source is where the river begins and the mouth is where it meets the sea. This, ladies and gents, is the source of the River Exe. You can just see, look, a little baby River Exe. In this part of the world where we are, most rivers begin as bogs up on high ground like Dartmoor or Exmoor, Bodmin Moor, etc. So they generally start as bogs, and then they will gradually trickle downhill. So here is a baby River Exe, very near the source. Look, there's the bog. And here is the mouth of the River Exe at, you guessed it, Exmouth. So, yeah, the source is where it begins, the mouth is where it meets the sea. And then it asks you to label the feature labelled A in figure 1. So a confluence is what it's called. A confluence is where a tributary, which is a small river that joins the main river. A confluence is where a tributary meets the main river. It's kind of like a river version of a road junction. That's a pathetic way to explain it, but that kind of helps. So source is where it begins, mouth is where it ends, tributary is a small river that joins the main river, and a confluence is where a tributary meets the main river. So just in case that caused you some problems. There are also, that is the drainage basin of the River Thames. So you can see that the River Thames is the main river, and all of these, look, are tributaries. So rivers often have huge amounts of tributaries feeding into them. Okay. Right, and there are some maths questions. We can't escape maths in geography. I know you might wish that we could, but we can't. There's one which shows you a dispersion diagram, and in case that is a new type of graph to you, this is a dispersion diagram on the screen. It's fairly simple, and it's used to show numbers, whether they're spread out or really, really clustered. Dispersal is like how wide an area does something cover. So what you do is you put a little dot or cross, and if you have two that are the same, you put the dots or the crosses next to each other. Now you probably have seen the finished result of a dispersion diagram. So what we usually do is we start off with a dispersion diagram and we turn it into, ta-da, a box and whisker or a box plot. So what you have to imagine here is that there was some original data, but we don't need it anymore because it's been superseded by the box and whisker. So the whiskers are the highest and lowest numbers. So you'd have your whiskers here and here. Then you have to work out your median, which is your middle number, and your upper and lower quartile, and that becomes your box. So you get your median and then you get your box. And hey presto, what box plots do is exactly the same as dispersion diagrams. They tell you whether your data is very spread out or actually very, very clustered. So yeah, just a couple of questions about that. Anywho, the first page that would be a good idea for you to fill in your module booklet if you're a student at our college There's a revision page on page 21 this year. It might be a slightly different page number in other years, called Causes of Excess Runoff. You may have heard me talk in previous videos about the fact that runoff is the process or the flow that we are most interested in, because it's a very, very fast movement of water, and that generally means that flooding is quite likely. It's worth just having a really good set of notes about why you tend to get excess runoff. So on page 21 this year, there is a table that says prolonged rainfall. And your best example of that is the Somerset levels. It wasn't particularly heavy rain, it just didn't stop raining. It was the wettest winter for 250 years. And if we think of the water cycle as a system, what that means is that your whole drainage basin is full up of water. There is nowhere left for the water. The groundwater's full, the soil's full, the vegetation's full, everything is saturated. Hey presto, you get loads of runoff. Hey presto, you get flooding. But it might just be intense rain for a short period of time. And Boscastle is your best example of that. So they got nearly 2 months of rain in 6 hours. Now that's not to do with everything being saturated, that's a speed issue. Water takes time to infiltrate, it takes time to percolate. If it can't infiltrate quick enough, it's going to start travelling over the surface of the soil. It's a speed issue. So what we're trying to say is here, you could either get a lot of runoff because it's been wet for ages, or you get huge amounts of rain in a short period of time. So although the end result is the same, the reason you have the runoff and the flooding is quite different. The third box talks about volume of rainfall, which could be either of those situations. So you could draw some arrows, or you could just copy them both into that box. Volume is just sheer amount. And you're going to get lots of rain, either because it rains a little bit for ages, or it rains a lot for a short period of time. Okay. Then it says monsoon rainfall. We're going to study the tropical monsoon in year 2, so you'll know a lot more about the monsoon then. But there are places that have rainy seasons, as you can see here, and the idea is exactly the same as what we said here. If you get huge amounts of rain over a 3 or 4 month period, the chances are you're going to see a lot of runoff in that time and potentially some flooding. Snowmelt. There is a video here if you want to see what a river with loads of melting snow in it is like, but you can probably imagine snow melt tends to happen quite quickly, and the problem with snow melt is that the ground underneath the snow is usually frozen solid. Therefore, no infiltration happens, it all travels as runoff. Okay, so snow melt is usually quite a serious problem for runoff and for flooding. That brings us to the second column. Urbanisation impermeable surfaces I talk about in other videos, so I'm afraid I'm going to refer you back to those. Drainage systems, soil compaction, deforestation, ditto. They come up in other videos. So I'm not going to repeat myself, but I do need to pick up on dam mismanagement. Dam mismanagement is the odd one out. Every other box in that table is about surface runoff. That one is about river runoff. So there's a little terminology point here. Surface runoff is water travelling over the surface of the land because it cannot infiltrate, whereas river runoff is water in the river. Now you don't need to know a lot about dam mismanagement, it's just one thing. So here is a dam open, here is a dam closed, pretty obvious. If you're not paying attention or you're not very good at managing your dam, you could make some bad decisions, and you could either lead to too much water in the river or not enough. Okay, and that's all you need to say. But remember, this is the odd one out. It is not about surface runoff, it is about river runoff. So you just need to kind of draw attention. And just so you know, I'm not making it up. If you have a look at that website, it will tell you that unfortunately dam mismanagement does happen. It's happened in India, it's happened in Australia, I think it's happened in Brazil. I promise I'm not making that up. It does genuinely happen. Okay, so just a little bit of revision before we get to, oh, there's those images again, just to remind you. Right, here's the meat of the video. The water balance. Okay, so the water balance is an equation, and you could be forgiven for thinking that I've got algebra on screen. I absolutely haven't. P stands for precipitation, obvious. Q stands for river runoff, the amount of water in the river. E stands for evaporation and evapotranspiration. Now, if I can drag your mind back to video number 1, precipitation is the only input to the water cycle. There are 3 outputs: river runoff, evaporation, evapotranspiration. All this is telling you is that the amount of water that comes in will equal the amount that comes out. And that's quite logical, isn't it? What the hell is this bit? Give or take, change in store. So let me show you some numbers for a minute. And I've completely made these numbers up. Let's say you had 1,000 litres of precipitation coming in to your drainage basin. Okay, 1,000 litres. And you measured your river and you found out that 600 litres came out of the river. And you measured your evaporation and your evapotranspiration, and 200 got evaporated. Well, there's 200 missing because 600 plus 200 is 800, but we had 1,000 litres of water coming in. Where the hell is the other 200? Well, after some research, you discover that 100 litres is underground, 50 litres is in the soil, and 50 litres is in the plants. Okay? The amount of water you put in will equal the amount that comes out, give or take what stays in the storage. And then suddenly it's not quite so scary. Now, in the class, I demo this with a beaker of water, and I pour lots of water in and out and stuff like that. And if you find this idea really complicated, I would actually urge you to kind of maybe demonstrate this for yourself with some water and a glass and, I don't know, probably a washing up bowl so you don't like flood the house and get in trouble. But if you're finding this quite tricky already, grab yourself those bits of kit and then you can kind of demo it for yourself. So the water balance is an equation. The amount that comes in will equal the amount that comes out, give or take what stays in stores. Okay. Most people usually stick with me up to that point. Might be a bit tricky. And then I show them these graphs and I lose quite a lot of you. So that's why I would urge you, if you think you might struggle or you remember doing this in class and you're like, yeah, I didn't get it at all, get some kit so that you can actually prove this to yourself, okay? Now, hopefully in class, you would have done some colouring already. If you haven't coloured in the graphs, here are the graphs that you've got in your module booklet. If you haven't got them, then I would suggest that you want to colour them in first and use the key. Obviously, you're going to have to sort of change the colours they use to match what you've got. If necessary, then you might want to take some photos of the screen possibly and do it that way instead. Okay, so these graphs are the graphical representation of this equation. They're very much linked. And yes, they are a bit confusing, but we'll get there, so bear with me. Right, grab your kit if you need it. Right. Water surplus is where you have more water coming in than going out. You have too much water. All right, so if you've got your glass and your thing, if you keep pouring until your glass is overflowing, you have created water surplus. And it's purely because you've got more precipitation coming in than you have leaving the drainage basin, so there is just too much water everywhere. Fair enough. Then, if you start tipping water out of your glass, so now the outputs are higher than the inputs, the amount of water in your glass is going to go down, isn't it? Because you've got less coming in and more going out. Just like you drinking your bottle of water throughout the day. You're using it, utilising it. So the amount of water is going down. It might get to the point where you run out of water. There is in fact none left, and we call that deficit. Now, before we can go back into surplus, we've got to fill our glass back up again, haven't we? Because if we've emptied our glass, or if we've used half of the water, to get back to the top, we've got to refill it. And in the water cycle, that's called recharge. So you could play around with your water and kind of get used to these words. But once you are used to these words, these graphs make a little bit more sense. First thing I will say, at their heart, ladies and gents, they are just climate graphs. You get the months of the year along the x-axis, January, February, March, April, May, etc. You get a blue line for precipitation. Notice my brilliant drawing skills here. And you get a red line for evaporation based on temperature. And this is a very bad version of what you expect in the UK. You expect there to be more precipitation in the winter, goes down in the summer, goes up again in the winter, and we expect summer to be hotter than winter. That's a pretty typical UK. Now keep that in your head. Look, months of the year, evaporation, precipitation. At its heart, it is just telling you what the climate of the place is like. Here, look, this is Ghana. They've got a rainy season, but it's hot all year round because they're near the equator. New York, it rains all year round, but it's hotter in the summer than the winter. Texas, it's blinking hot and they don't have a huge amount of rainfall. So if you get really stuck with these, fundamentally come back to the fact that they are just climate graphs. They're just trying to give you a sense of how much precipitation a place receives and what temperature it gets in the different months of the year. What we then do is we colour them in, and we colour them in to try and give a sense of what situation is happening in terms of the water balance. Is there too much water everywhere? Surplus. Is the water being used up? Utilisation. Have you run out of water? Deficit. Or is your water store all filling back up? Recharge. So if we look at the UK, let's start in January. Precipitation is high, evaporation is low. We have more water coming in than going out. Hey presto, surplus. And we stay in that situation, look, until about the end of April, the beginning of May. We have too much water. In April, May, there is a transition. Evaporation goes above precipitation. We now have more water coming out than going in. So this is like you drinking your bottle of water over the course of the day. Gradually, the amount of water is going to go down. You are using the water up. So when we get into September, October time, and the precipitation is higher than the evaporation, we cannot immediately go into a period of surplus because we've got to refill our drainage basin. If you've spent all day drinking out of your water bottle, before it's going to overflow, you've got to fill it back up again. And that is what this section is. All of the stores of your drainage basin need to fill back up with water, and then eventually you will get to surplus again. And what this tells us, it's a predictive tool. It tells us when we might get floods in the UK. It tells us when we might need to get water from other sources. We might begin to run out of water. Unlikely in the UK, to be honest. Flooding is very unlikely at these times because we wouldn't be in a period of surplus. So we use these to predict what will be going on with regards to the water balance. I appreciate that some of you will just be like, whoa, this is too much. You can pause, you can fast forward, rewind, come back to it again, but at their heart, remember, come back to the fact that they are just climate graphs and you shouldn't go too far wrong. Now, the problem for you is that every single part of the world, of course, has its own version because every part of the world has its own climate. And once you've cracked these, and I'm sure that you will get there with patience and determination, once you've cracked these, they can give you a water balance graph for anywhere in the world and you'll be fine because you'll be like, oh yeah, I know what that means. So if maybe this is enough for today, just get familiar with what those words mean, okay? And if that's enough for your first bite of the cherry, great. And then you can come back to this another day and kind of persevere with it. You may have noticed in the UK graph, we didn't have deficit. We don't run out of water in the UK very often. It's a very, very weird thing for us to do. In Ghana, they spend most of the year in deficit, i.e. there is no water left. But as long as you know what these terms mean, you can interpret this graph. So you can say, so in September, October, there is more precipitation than evaporation. So there is surplus water in Ghana. It's a possibility they might have a flood at that time of year. Then, October, November, they go into utilisation. The water is being used up. Evaporation is higher than precipitation. The amount of water in your drainage basin is going down and down and down and down until they get to December and they have run out of water. Their drainage basin is dry. And then we get to July, whereby precipitation is higher than evaporation and everything can fill back up again and you go into surplus. So there is a sequence to this and it's all about these. Right, final pair. Salisbury in New York, and yes, this is not Salisbury, UK, this is Salisbury, New York. There's a Taunton in America as well, and Manchester, lots of places. Look, this is easy. If precipitation is higher than evaporation all year round, they are always in water surplus. It's not a lot to say. Flooding would be least likely here because there's only a small difference, and it would be really likely here. Texas, very different part of America. In fact, there is no water surplus at all. Look, they're either in deficit, utilisation or recharge the whole year. So these are a bit tricky. They might take time, but remember a couple of things. The most important thing is to understand what these words mean for the amount of water. The second thing is to remember that at their heart, they are climate graphs. And then the third thing to remember is that they all link back to this. The amount of water coming in will equal the amount coming out, give or take what you leave in your stores. Right, that's the tough stuff over. Nice and quickly now at the end of this. Some places, as I've mentioned, run out of water, and if you've got a college module, there is a space for notes on this. Why do some places run out of water? That is a jolly good question. Well, Ghana, which we've already talked about, a country in West Africa, they run out of water because it doesn't rain all year round. In the UK, it rains in every month of the year, so it's highly unlikely, although not impossible, as I'm about to tell you, it's highly unlikely that we would run out of water because precipitation falls out of the sky all year round. Some places in the world have seasonal rain, i.e. it doesn't rain all year round. And if it doesn't rain all year round, you're probably going to run out of water. If I said to you, in your house, you can only turn the taps on at these times of the year, even if you filled every saucepan, the bath, every possible bucket with water, chances are by about February, you'd probably have run out. And that's it. If it doesn't rain all year round, your chances of running out are quite high. Now, it's not impossible for us to run out of water in the UK, and the last time it happened was 1976. We had a serious heat wave. Sorry about the quality of this graphic. So we saw 15 consecutive days where temperatures reached 32 degrees or above. And in the southwest where we are, we went 45 days without rain. You can't even imagine that, can you now? So a proper heat wave. Most of the UK received significantly less rainfall than usual. Our rivers ran dry, and our reservoirs, villages that had kind of been flooded at the bottom of reservoirs, don't worry, the people were evacuated first, eerily appeared out of the bottom of these reservoirs as the water ran out. So it was really weird. There is a little BBC News clip about what happened. You can just have freak weather events, which means you run out of water. But the last time it happened in the UK was 1976. So it's not common for us at all. Unfortunately, we have this horrible old thing called climate change. Climate change is affecting precipitation patterns massively. I could have used the Australia bushfires. I could have used the Greek forest fires. I chose California, but you could easily substitute for one of the other two if you would rather. And it's a really simple concept, ladies and gents. Climate change means it rains less. Now, if you're thinking, okay, I get that, why does that lead to fire? It's because dry plants and dry wood catches fire really easily, whereas wet wood doesn't burn. If these forests and these places were normal and they were full of water, they wouldn't have caught fire. But because there's been hardly any precipitation and everything is so dry, they catch fire incredibly easily. But they don't catch fire spontaneously. It's not spontaneous combustion. So usually these forest fires can be tracked back to somebody chucking a cigarette on the ground, or a car accident in which the car caught on fire. So they don't spontaneously combust, but once the fire has started, because the forests are so dry, the fire just spreads and goes absolutely mad. But climate change can lead to drought and deficit. And then finally, we're going to blame humans. This has been rectified, I would just like to say. Coca-Cola got kicked out of India and the situation is improving. Coca-Cola obviously make drinks. To make drinks you need quite a lot of water, and humans take water out of the ground. So before Coca-Cola built their bottling plant, you would have to dig a well about 8 metres underground to access water. When they left, you would have to dig your well to about 38 metres to get any water out of the ground. So humans, if we take too much water out of the groundwater store, we can begin to cause deficit problems for ourselves. It's not just Coca-Cola at all. They are just the best known example of this happening. But farmers do this, towns do this, it is... Many other companies do this. It's not just them, it's just that there is absolute proof that it did happen in India because of Coca-Cola. But yeah, humans take too much water out of the ground and that could lead to deficit. Okay, final bit of the video. This has been quite a long and intense video for you. The other reason that you could end up with a little bit of deficit is because of impermeable surfaces, weirdly. Aquifers, or the groundwater store, is water stored underground. That's pretty obvious, I would think. How does it get there? Well, you have to infiltrate the soil, percolate the rock. If you have managed to cover all of this area in impermeable surface, you're not going to get infiltration or percolation. So your aquifer or your groundwater store is not going to fill back up again. Okay, and I'm sure you appreciate that we have this thing called urbanisation and urban growth, whereby lots of people are moving to towns and cities and they're getting bigger. And one of the key things about urban areas is they are full of impermeable surfaces. And as humans spread out across the planet, we are stopping these aquifers from refilling because we cover them in impermeable surfaces. Which means, firstly, we are not helping ourselves with deficit problems, because if you're not able to top up your aquifers, you're not able to refill your groundwater store, then that's not going to help with deficit problems. And it's got to the extent that in London and other places, but London is one of the best known examples, we actually have to refill our aquifers artificially. London is obviously a very big urban area. It has huge amounts of impermeable surfaces, and it's impeded the infiltration and percolation to the extent that the Water Board have to recreate Aquifer Recharge. Very simple process. You essentially dig a well, and instead of taking water out, you put it in. It's not a complicated procedure. It's just rather shocking, perhaps, that we have to do that because we have, messed around with the water cycle so extensively. Well done for surviving that, folks.